Okay, so welcome back everyone to this next edition of the String Pheno seminars. Today our first speaker is going to be Giorgio Leone from University of Turin, and he's going to be talking about rigid Orientifold Vacua in 6D with broken supersymmetry. So please just go ahead and share your slides, Giorgio.
Yes. Right. Can you see it?
Yes, perfect. Great. Then the floor is yours. Please go ahead.
Okay, thanks. Well, thanks, Matilda, for the introduction, and also thanks to you, Alvaro and Damian, for the invitation. I'm very happy to be to present the work that I've been doing with Carlo Angelantoni, Cesar Condescu, Emilian Dudas. It has appeared recently on the archive. The presentation of today is going to be about some new solution that we have found for Orientifold Vacua in 6 dimensions, obtained from K3 orbifolds, in which supersymmetry is broken in such a way to avoid tachyonic instabilities, and which such vacua are characterized by the fact that the possible deformation to be performed are actually very limited in the way I will be describing in the following. Let me start by giving you some motivation. And of course, studying non-supersymmetric string vacua is a well-motivated task, both from a phenomenological but also from a conceptual point of view, and has received much of attention in the last decades, and also to which many people connected today have contributed to. And it has become clear that string theory provides many ways through which such non-supersymmetric vacua can be actually built. Here, there is a list of some of the possibilities, which is by no means complete. But for instance, one can choose to start with a non-supersymmetric vacua in which supersymmetry is absent by the choice of the GSO projection, as it happens, for instance, for the non-supersymmetric heterotic models or the type 0 superstring models and their related Orientifolds. Or one can start from a supersymmetric model and then break supersymmetry by the effect of compactification, such as choosing a proper internal manifold or turning on magnetic fields, or employing a freely acting orbifold, such as a Schwarz compactification. But the mechanism through which we're going to break supersymmetry, on which this presentation is based today, is a bit different, and in particular involves non-trivial Orientifold projection of the type 2b superstring, in which the consistency of the vacuum requires the introduction of objects that break supersymmetry, loosely speaking. This is what happens, for instance, in the Sugimoto model, and of course in the Brane Supersymmetry Breaking vacua that I will describe. One of the most interesting features about these models is the fact that if most of non-supersymmetric string vacua admit a region of the moduli space in which tachyons emerge, the Sugimoto and BSB models actually have no such tachyonic instabilities. So the plan of the talk today will be exploring this new solution that we found for Brane Supersymmetry Breaking vacua. But before doing that, I would like to give a brief discussion about the Sugimoto vacuum in 10 dimension, since most of the features that will appear in the Brane Supersymmetry Breaking vacua are already present for the Sugimoto model. And here we have the advantage that we are dealing with a more a simpler scenario, and therefore I hope that some of the features will be clearer in this context. So let me start by discussing the Sugimoto vacuum in 10 dimension. This is actually obtained through a Orientifold projection of the type 2b superstring, in which the worksheet parity operator identifies as fixed points Orientifold planes that fill the whole space-time, so that are O9 planes, and carry positive tension and charge. The consistency of the vacuum requires to introduce 32 anti-D9 branes which cancel the Ramon charge of the non-dynamical tenform appearing in the vacuum. And this object, the O9 planes and anti-D9 branes, are BPS objects, but preserve different set of supercharges, and therefore supersymmetry is broken. A hint of the fact that supersymmetry is actually broken in this model is given by the uncancelled Neve-Schwarz dipole, which encodes the tension of the Orientifold planes and the anti-D9 branes, which is both positives, are both positives and therefore cannot be cancelled against each other. This is translated into the usual runaway behavior of the dilaton potential, in which there is a non-vanishing contribution arising from the uncancelled Neve-Schwarz dipole. The breaking of supersymmetry is actually manifest when studying the spectrum, of course. And here, even though in the closed-string sector, we have a supergravity multiplet for the minimal amount of supersymmetry in 10 dimensions, in the open string sector, supersymmetry is actually broken, since the gauge bosons and will-be gauginos transform into different representation of the gauge group. As things stand now, there seems to be a puzzle with the consistency of the vacuum, because on one hand, we have a supersymmetric closed-string sector at tree level, and on the other, we have, but in a setting in which supersymmetry is actually absent. So it seems to be impossible to write down a consistent interaction term for the massless gravitino, because it will require to couple the massless gravitino with a conserved current, which in supergravity is the supercurrent. But since we don't have supersymmetry, such term seems not to be possible to write it down. This puzzle was actually solved by Duda Simorad in 2000. When they noticed that the singlet that appears in the representation in which the will-be gauginos transform actually corresponds to a massless Goldstino that reflect the fact that here supersymmetry is spontaneously broken, but since there is no order parameter that can recover the symmetry, such breaking has to be thought as occurring at the string scale. In this sense, supersymmetry is not absent, but not linearly realized. And therefore, this solves the puzzle because it is possible to write down a consistent interaction term for the massless gravitino. So this captures more or less the main features of the Sugimoto vacuum that will be relevant also for the discussion of the Brane Supersymmetry Breaking Vacua. And to summarize, Brane Supersymmetry Breaking is induced by a non-trivial Orientifold projection that flips the tension and charge of all the Orientifold planes at our disposal, which are O9 planes. But when studying compactifications, of course, we have more possibilities. For instance, in the following, we will be focusing on Orientifold obtained from criteria orbifolds of T4 of type T4 over Zn, in which the standard worldsheet parity operator is dressed with the point group defining the orbifold, and this identifies additional Orientifold planes which fill the whole non-compact space-time but are localized in internal manifold. Now, one has the freedom to flip the tension and charge of only a subset of Orientifold planes by choosing a proper non-trivial involution that tacks on the twisted two cycles. And indeed, if this non-trivial involution, if this involution acts non-trivially, then we are identifying Orientifold planes with negative tension and charge, the 9 ones, and Orientifold planes which have instead positive tension and charge, the O5 plus planes. For the consistency of the vacuum, then we are required to introduce D9 and anti-D5 branes, and therefore, for the same argument as before, the simultaneous presence of O5 plus planes and anti-D5 branes break supersymmetry. This configuration is what in literature is known as Brane Supersymmetry Breaking. And let me just notice that this configuration cannot be obtained by a simple compactification of the Sugimoto model, because for the Sugimoto models, all the Orientifold planes have flipped tension and charge. But here, only the O5 ones have a a positive tension and a positive charge. Also, let me notice that if the involution acts trivially on the twisted two cycles, then we are identifying Orientifold planes and with negative tension and charge for the both type, which requires the presence of D9 and D5 branes, which realizes the minimal amount of supersymmetry in 6 dimensions. And this construction corresponds to the usual one known in literature by Dimon and Polchinski and Double-Karen-Park and so on. So this is more or less the idea behind Brane Supersymmetry Breaking Vacua. And now what I would like to do is to show you how this works concretely by discussing some concrete models. In particular, let me start with the base B Orientifold obtained from the T4 over Z2 orbifold. This corresponds to the regional construction made by Antoniadis, Tudas, and Sagnotti in 1999. And here, the Z2 action of defining the orbifold transform the complex coordinates parametrizing the two tori in the following way, and identifies 16 fixed points indicated here by the red dots. The non-trivial Orientifold projection now identifies Orientifold planes, which are given by the usual O9 ones, and 16 O5 planes with positive tension and charge, which are placed on each orbifold fixed point. This Orientifold projection, therefore, on one hand, it allows to compute the spectrum, which organizes into suitable supermultiplets for the minimal amount of supersymmetry in 6 dimensions. And on the other hand, identifies Orientifold planes which have a non-trivial charge only for the untwisted Ramon-Ramon 6 forms that appear in the spectrum. Therefore, to require the consistency of the vacuum, we have to introduce D9 and anti-D5 branes to cancel the Ramon-Ramon tadpoles, and we can do so by choosing 2 different options. In particular, we can decide to place all the anti-D5 branes on a single fixed point. This actually corresponds to the original construction made by Antoniadis, Tudas, and Sagnotti in 1999. Or we can choose to place the anti-D5 branes over all the Z2 fixed points, which corresponds to the variation, the almost rigid variation that we have discussed in our paper. Before starting the discussion of these 2 configurations, let me just remark once again that the Orientifold planes have a non-trivial charge only for the untwisted Ramon-Ramon 6 form, while the twisted charge vanishes, and it is indicated here with a 16-dimensional vector. This is going to play a crucial role in what follows, and it is something that we have to keep in mind. So we can start discussing the anti-D5 branes placed on a single fixed points, which correspond to the vacuum discussed by Antoniadis, Tudas, and Sagnotti in 1999. And this actually yields a gauge group which is of the following form. And you can see that supersymmetry is broken in the open string sector by the presence of the anti-D5 branes, since gauge bosons and would-be gauginos transform into different representation of the gauge group, and also scalars and symplectic Majorana-Weil left-handed fermions transform as well into a different representation of the gauge group. As before, we have would-be gauginos that transform into a reducible representation of the gauge group for the anti-D5 branes, and this provides the Masters-Goldstino, which reflect the fact that also in this case supersymmetry is broken at the string scale and actually not linearly realized. And this is discussed extensively by Pradisi and Riccioni in 2001, in paper in 2001. As for the Sugimoto model, we have an untwisted, an uncancelled Neves-Schwarz tadpole that comes only from the untwisted sector, which contributes to the dilaton potential in the following way. and in which you can see that the non-vanishing term only comes from the anti-defied branes. The situation actually changes a bit when placing anti-defied branes on all the Z2 fixed points. And in particular, in such a case, again, supersymmetry is, in such a case, the gauge group is now modified, and supersymmetry is actually broken in the same way as the standard solution that I discussed a few seconds ago. And still will be gauginos transformed into in the singlet, which denotes the fact that supersymmetry is broken at the string scale and non linearly realized. But the important point to notice in this vacuum is the fact that we don't have light states transforming into bifundamental representation of the anti-defied gauge group. This has a straightforward geometric interpretation because strings that are stretched between different anti-defied branes can only yield massive contribution because anti-defied branes are placed on different fixed points. But this means that we have no scalars transforming into bifundamental representation of the anti-defied gauge group, and therefore we cannot partially recombine branes, so that we cannot recombine anti-defied branes via Xing to move anti-defied branes away from the fixed points. Still, since the Orientifold planes carry no twisted charge for the encoded here, we can still recombine all the D-branes together to move them into the bulk and then recombine back to the standard solution discussed by Antoniadis, Vacua, and Sagnotti. So that in this sense, this model is not truly rigid, but it can be connected via an overall brane recombination to the standard solution. Another interesting feature of this vacuum is the fact that right now, the diatom potential does not only receive a contribution from the untwisted tadpoles, but receives contribution also from the twisted ones by the uncancelled tension of the D-branes. Here, this psi A appearing here are scalars in tensor multiplets localized on the fixed points. And it will be really interesting to study the dynamics of this vacuum better, because a non-trivial vacuum expectation value to these scalars would imply a resolution of the orbifold singularities. And therefore, it will be interesting to understand if such resolution can be described dynamically in this vacuum. So this was the situation for the Z2 orbifold. And when moving for the Z4 to the discussing the Orientifold, the BSP Orientifold for the T4 over Z4 orbifold, we see that the situation changes quite dramatically. In such a case, the Z4 point group action acts in the following way with a rotation of 90 degrees on the two tori, which identifies 4 fixed points, which are here indicated with the red dots, and the Orientifold projection with the non-trivial involution identifies O9 planes which carry the same set of charges, loosely speaking, as the Z2 model. But there is a crucial difference with respect to the previous case. This is given by the fact that the O5 plus planes, which are localized on the Z4 fixed points, now carry a non-trivial twisted charge. This means that in order to guarantee the consistency of the vacuum, we have to introduce anti-defied branes on the Z4 fixed points in order to neutralize the charge of the Orientifold planes locally. So if for the Z2 case, placing anti-defied branes over all the fixed points was a choice, and such freedom is reflecting to the fact that we can actually connect this solution to the standard one in which all the anti-defied branes are placed on a single fixed point. For the T4 over Z4 vacuum, placing anti-defied branes over all the fixed points is mandatory. Another interesting feature of this solution is given by the fact that there is not a unique solution to the Ramon-Ramon tadpole condition, and indeed, it is possible to cancel the Ramon-Ramon tadpoles in a non-trivial way, which identifies a family of gauge groups parameterized here by M, which you can take value from 0 to 2. Giving rise to vacua which are a priori disconnected. Actually, this observation is not new in the literature, but it has already appeared in the paper by Addazabar and collaborators, in which, however, they discuss Orientifold construction in a supersymmetric setting in 4 dimensions. But it's also interesting to notice that this fact is not intrinsic of Brane Supersymmetry Breaking vacua, but applies to supersymmetric construction as well. So, as before, supersymmetry is actually broken in the open string sector. And again, we don't have light states transforming to be fundamental representation of the anti-defined gauge group. And this means that we cannot recombine anti-defined branes to move them away from the fixed point by giving a non-trivial vacuum expectation values to the scalars. This has straightforward geometric interpretation again, since moving anti-defined branes away from the fixed points would leave an uncancelled Ramon-Ramon tadpoles, which are encoded, which are given by a non-trivial charge of the Orientifold planes, which lie on the Z4 fixed points. And therefore, such recombination is forbidden. But the fact that Orientifold planes have a non-vanishing twisted charge also forbids the overall recombination that was previously allowed, since, again, moving all the D-branes into the bulk would leave an uncancelled Ramon-Ramon charge and would lead to an anomalous model. So finally, let me just comment on the scalar potential that arises from this BSP vacuum. And in particular, one can see that, as before, we have a contribution arising from the untwisted tadpoles here, and a contribution arising from the uncancelled tension of the D-branes. And if the latter term is ubiquitous for all the solutions, the term, this term here vanishes for m equal to 2. So this was more or less what I wanted to tell you today. So let me just summarize what we've discussed and give you some future outlook that could be pursued. In particular, we have seen how BSB orientifolds provide a way to break supersymmetry, avoiding tachyonic instabilities. And we have explicitly discussed the 2 variations of the standard solution, in which anti-defined branes are placed on all the orbifold fixed points. And we have seen that such solution is almost rigid, in a sense that can be connected to the standard one via an overall brane recombination. The situation is different for the Z4 case, in which the presence of Orientifold planes with a non-trivial twisted charge forbids any recombination of anti-defined branes, and therefore, in this sense, the model is truly rigid. Of course, it will be really interesting to study the dynamics for this kind of vacua, and to understand whether it could be a dynamic mechanism through which the orbifold singularities can be resolved. Also, one can try to extend the result to the 4-dimensional case, and one can try to study the consistency of this vacua under more general kind of anomalies, which test the consistency of the vacuum under topology changes, so-called Dayfried anomalies. And so with this, I would like to end my presentation, and thank you for your attention.
let's all thank Giorgio for a great talk. And if anyone has any questions, please just go ahead and unmute yourselves. Oh, maybe as people think of a question, I can ask a quick one. So I guess I'm curious because so depending on which case you're talking about and where the Orientifolds were, you had these scalar potentials in lower dimensions that were like that had more structure, and you said, okay, potentially like some of the moduli could get vevs. So could you stabilize all of these extra moduli, or could you could never, I guess, stabilize the dilaton, right? It's always going to be a runaway, or
well, the fact is the fact having this non-trivial potential tells you that actually a maximally symmetric Minkowski vacuum is not allowed as a solution, and one should actually try to solve find a solution to the equation of motion in order to that it is going to tell you that you have a system a stable vacuum for this model. But the dynamics of this kind of vacuum with this potential, actually, we didn't carry it out, and actually, I don't know. It's just that it will be interesting to understand whether there is a possibility that somehow these scalars can get a non-trivial vev, so that to resolve the orbifold singularities. But yeah, the analysis is quite complicated, and we didn't carry out yet.
So no matter what you do with these O-planes, you always have just more runaway potentials, just more kind of runaway contributions to the potential. You can never get a minimum.
Well, you have to, in this setting, yes, but you have to study, you have to find a solution and then see the feature of the solution.
I see. Say. Great. Yeah, thanks. That's great.
Hi, Giorgio. Thank you for the nice talk. Could I ask
yes,
one question? So I'm trying to understand better what non-linearly realized supersymmetry means here, because here we're talking about a gauge symmetry that's being broken at the string scale.
Supersymmetry is broken at the string scale.
Right, but in a supergravity theory, the bulk theory.
Oh, sorry, I'll finish you. I'll let you finish.
Okay, maybe that's the question. Is supersymmetry gauged here, or are you thinking of it as ungauged?
I'm thinking about okay, the point is that supersymmetry here is broken at the string scale because as I was saying before, you don't have like an order parameter to that can recover the symmetry in a sense. So here the presence of the master Golstino tells you that actually supersymmetry has been spontaneously broken, and this breaking appears at the string scale. So yeah.
Okay. So if I think about a normal kind of Higgs mechanism where I'm breaking in some global symmetry initially, and then it's getting eaten by some gauge fields. Normally, I wouldn't see the Golstino in the low energy action. So why? I guess I'm confused about why there's a Golstino at all in the story.
Because when you spontaneously break in supersymmetry, a master's Golstino appears in
global supersymmetry. But in supergravity, I would expect the gravitino just to get massive.
Okay, I'll think more about it and then.
Yeah, I mean, it's really a question of sort of in the low energy action, is there a symmetry that one can see as an implication of having non-linearly realized supersymmetry?
Yeah, but okay. Yeah, but actually you can writing in this paper by Dudassi Murad for the Sugimoto case, to be specific, they write down low energy effective interaction and all the possible transformation of the fields under this nonlinear supersymmetry, in which this Golstino plays the role of the Volkov-Akul field, so to speak. And you can write down all the transformation and see that actually the action is invariant under this transformation.
Okay, so there's an
So
explicit.
you can see it
normal there.
directly at the level of the Lagrangian.
And that symmetry should be preserved. It should be preserved by quantum effects then, presumably.
Yes, yes,
Yeah.
I would say so, because otherwise, as it would be inconsistent to write down a massless gravitino to be the interaction term for the massless gravitino, I would say.
Yeah, yeah. I'm just confused about why it stayed massless. That's the thing that was puzzling to me. Okay, great. Thank you.
You're welcome.
Maybe one last quick question from MPP.
Hi, yeah, actually, I just wanted to maybe add something on the previous question by Sav. So the the story about the super Higgsing in these settings where SUSY is broken at a string scale, right, where it cannot be captured by an effective field theory description. It seems to be that perhaps it could be captured by, like, the super Higgsing mechanism could happen in a lower dimensional setting induced by the scalar potential, right? Like because there is no, as Giorgio pointed out earlier, there is no maximally symmetric flat space-time background in this setting. There is an old paper by, I think, Sagnotti, Dudas, and Murad, where they emphasize that the counting of degrees of freedom that could allow for a massive gravitino could occur in lower dimensions, but not in the highest dimensional sector. So the story is a bit complicated, but the point is that it is expected that a super Higgsing does happen, but just not in the easiest possible way, let's say.
Okay.
Just wanted to point out.
Great, no, thank you. If there are no other immediate comments, I can also leave the Zoom open after the second talk if you guys want to discuss a bit more. But anyways, let's thank Giorgio for the great talk again. And let's move on to our next speaker.